Hi guys, Rob from Royal Balls, part 3 of our genetics series. What would genetics be without looking at some really cool snakes? This is where genetics starts to get interesting. So today we're going to look at multi-gene combos, we're going to look at working with hets, but we're going to use real world projects that I'm working on. So let's get cracking. The first example I'm going to use is this female snake here. Was produced by me last year, and this is a Pastel Pied. This is a female, and you can see just how bright yellow she is. But as she's got older, the sides have got a little bit muddy. You can see the muddying along the sides here. So I thought it would be really cool as a little co-dominant or incomplete dominant project that I can get some really fast results from, to try to clean this snake up. So what I want to do is to pair this Pastel Pied to my Firefly male, and you can see the contrast and the brightness of this guy and how much cleaner the sides are. This is a really nice combination, Fire Pastel Pied. So this male will go to this female either early next year or late next year, depending upon the size. But let's just frame that in terms of the genetics involved. So we have, on the male side, we have Pastel and we have Fire. One copy of each gene on the male. On the female side, we have Pastel and we have Pied, and you'll see that the Pastel gene occupies exactly the same slot on the male and the female, but both the Pied and the Fire occupy different addresses on the genetic material. So we'll introduce one new concept to our talk on genetics, and that's the lack of dependency. There is no dependency between the genes. Just because you get Pastel doesn't mean you're going to get Fire. Just because you get Fire doesn't mean you're going to get Pied. Each of the genes acts independently and there is no dependence between them. Okay, so when we pair these snakes up, we can already see that we have a Pastel in both parents. So the outcome could potentially be Super Pastel. So let's work the genes independently. So we'll take a look at the Pastel in the parents first. We have one copy of Pastel in the female and we have one copy of Pastel in the male. We split the genetic material in half, so half of the female Pastel gene is going to be passed on to her offspring, half of the male. So here are the potential outcomes. This half of the male to that gives one copy of Pastel from the male, none from the female. This to that gives the super form, Super Pastel, 2 copies, one from each parent. Take the other half of the genetic material from the male and we get no copies in this square, and we get one copy from the female, no copies from the male. So in this particular outcome for Pastel, we have a 25% chance of a normal, a 25% chance of a Super Pastel, and a 50% chance of Pastel. So I'm going to write that down on my score sheet. Okay, we have multiple Punnett squares here, and if you like to work in fractions, each of these squares represents a quarter of the total, or 25%. So for Pastel, this is Pastel. Let's just transfer the outcome into this square. Okay, we'll slide that out of the way. That's Pastel dealt with. Let's remove the Pastel gene. And now we're going to look at fire. Remember, the male is a firefly, pastel fire. So the male has one copy of the fire gene, the female has no copies of the fire gene. So in this particular case, we have this half of the male to that or to that, gives us one copy from the male, no copy from the female, one copy from the male, no copy from the female, and the other half of the male genetic material, which doesn't carry the gene, gives us 0 and 0. So in this case, we have a 50% chance of the babies being fire and 50% chance of the babies being normals. So again, we'll transfer that into our matrix. So one copy, one copy. This is pastel, this is fire, and now we look at Enchi. One copy of the Enchi gene in the female, no copies of the Enchi gene in the male. And I think you can see that the outcome is going to be the same as for fire, with only one copy. So when we work the numbers, no copies in the male, so we get one copy, no copies, one copy, no copies, no copies, one copy. So again, the outcome is 50-50. 50% of the babies will carry the Enchi gene and 50% of the babies will not. So again, we'll transfer that outcome to this square here. And remember, the desired outcome for this pairing, let's get the snakes out again, what we were shooting for was a pastel Enchi fire, a combination of these two guys, to clean up what is already a very attractive snake here with the pastel Enchi. A super pastel Enchi fire might also be a good combination. That is one of the possible outcomes, but the desired outcome was to get the pastel Enchi fire. So what are the odds in that pairing of getting a pastel Enchi fire? Well, pastel has a 50% chance of getting the pastel gene into one of the babies. So that is the percentage for pastel. There's also a 50% chance of getting fire, and there's also a 50% chance of getting Enchi. So when you multiply those together, 50% of 50% is 25%, 50% of 25% is 12.5%. How about the super pastel Enchi fire? Well, the super pastel occupies only one square, so you have a 25% chance of one of the babies carrying both of those genes, 50% and 50%. So right there, we've halved our odds. When you multiply them together, super pastel has a 25% chance, fire has a 50% chance, and Enchi has a 50% chance. So this is 25% times 50%, which is 12.5%, times 50%, which is 6.25%. If you prefer it in fractions, it's a quarter times a half, which is an eighth, times a half, which is a 16th. So 6.25% or 1/16th chance. It's the same thing but expressed a different way. So we have half the chance of getting a super pastel Enchi fire as we do getting the pastel Enchi fire. And that's how we use the genetic calculator to work out those odds. So all we're doing is stacking the 3 genes at play and using that calculation of 4 different outcomes 3 times. You multiply them together and that's your odds. So you can always work out in your pairings what the odds are of getting your desired outcome. So that's a codominant project, and you will see that in that pairing there is a chance of getting your desired snake in the clutch of eggs that you produce. First generation. You will get that snake in the first generation. Now let's look at a recessive project and see what the difference is. Okay, let's move on to something a little bit more complicated, something a little bit longer term. In my collection I have two adult piebald ball pythons. I have one Pastel Pied male who has bred several times already, and I have one normal pied female. What I'd like to do is to create yellow belly pieds. Now, I think as you've seen from the genetic calculator, if I breed my Pastel Pied to the normal pied, all of the babies will come out pied, but how do I get yellow belly into the mix? Well, as we discussed in part 2, I'm going to need to create hets. So what am I going to pair with my pied, one of my pied breeders, in order to get the yellow belly hets? So let's take a look at the male. The male I'm going to use is the Pastel Pied male. Here he is. He is already mature and has bred several times. He's a really nice example, medium to low white, so you get to see plenty of pattern, the blushed sides. Just a beautiful animal. Wouldn't it be nice to get yellow belly into this too and really brighten up those yellows? So that's the objective of this project. So we'll use him as the male, so he is a Pastel Pied. In our genetics calculator, this is the male, and he is carrying 2 copies of the Pied gene and 1 copy of the Pastel gene. So that's the male. The female is not up to size this year, but should be up to size next year. She's rapidly approaching 1500 grams. This is a silky way, or a leopard ivory. Ivory being super yellow belly. So this is the super form of yellow belly, and the reason that I've chosen this female is exactly because she is a super form. So I am guaranteed that any of her offspring will carry the yellow belly gene, which is what I'm after. If I'm trying to create hets, I might as well increase my chances of getting the correct combination in the offspring by using the super form. So this is a super yellow belly female. So let's take a look at what she looks like in terms of our genetic calculator. So the female is a super yellow belly. She is carrying 2 copies of the yellow belly gene, and she's also leopard. She's carrying 1 copy of the leopard gene. And as we've discussed, all of these genes work independently. So we can look at pied first, we can look at pastel, we can look at yellow belly, and we can look at leopard. So 4 genes at play this time, one of which is a recessive gene, which is the pied. So let's take a look, first of all, at the pied part of the equation. So he's the male, he is a visual pied, so he's carrying 2 copies of the gene, and there are no copies of the pied gene in the female. So we know automatically that all of the offspring are going to carry 1 copy of the pied gene. So this half of the male or this half of the male, doesn't really matter. Each of his offspring is going to be carrying 1 copy of the pied gene. So let's transfer that to our matrix. This is pied at the top. So we're automatically guaranteed that all the offspring from this pairing are going to be 100% het for pied. Let's take a look at yellow belly. Yellow belly is the super form of the codominant gene. The female is the one that's carrying 2 copies of the gene, and again this acts in exactly the same way as the super form or the homozygous form of the pied gene. There are 2 copies, so the outcome is going to be exactly the same. Each of the babies will receive 1 copy of the yellow belly gene from the female, but not from the male. So here's the male without any copy of the yellow belly, here's the female with 2 copies. So again, doesn't matter which halves of the genetic material you combine, you are going to get 1 copy of the yellow belly gene. Now, when we talk about the pied gene, the 100% hets are not going to have a visual expression, but now we're dealing with a codominant gene. So each of these babies here receives one copy of the yellow belly gene and will look like a visual yellow belly. So let's transfer that to our genetic calculator. This is yellow belly. There are two other genes at play, one in each of these animals. So there's pastel in the male, so one copy of the pastel gene in the male, no copies in the female. So the outcome here is going to be 50%. 50% with the gene, 50% without. So if we look at the pastel gene, you're going to have two out of 4 babies will carry the gene, 2 out of 4 babies will not. So let's transfer that to our genetic calculator. Okay, so this is 100% chance of the babies carrying one of the pied genes, 100% chance of the babies carrying the yellow belly gene because they're both superforms or homozygous, 50% chance of the babies carrying the pastel gene, and again, if we look at leopard, the female has a copy of the leopard gene, the male does not. So one copy of the leopard gene in the female. So again, that's going to be the same outcome. 50% of the babies will carry the gene provided by this half of the female, and 50% of the babies will not. So if we look at that, let's use a different color. This is leopard. So that's the outcome there. 50% with, 50% without leopard. So let's put that onto our genetic calculator. So we have pied, one copy. We have yellow belly, we have pastel, and we have leopard. The desired outcome for us was to produce 100% het pied with the yellow belly gene. And looking at this calculation, there is a 100% chance all the babies will carry one copy of the pied gene, so they'll all be het for pied. 100% of the babies will carry the yellow belly gene, so they will all be 100% yellow belly het for pied. All the babies will be a minimum of yellow belly het for pied. So all of our babies actually satisfy our requirements, and that's because we used the super form of yellow belly. If we just used a single copy of the yellow belly, we would have reduced our odds by 50%, only half of the babies. Okay, so that's the desired outcome, but there are two other genes in play as well, so we have to consider the possibility that those other genes will be involved as well. So in this case, we don't want the pastel and we don't want the leopard in the mix. We just want a yellow belly het pied. So what are the possibilities that it is not going to carry the pastel gene? It's going to be 50%. What are the possibilities that it's not going to carry the leopard gene? It's going to be 50%. So when you multiply these out, it's 1 times 1 is 1, times a half is a half, times a half is a quarter. So a quarter of the babies will be just yellow belly het for pied. That's 25%, okay? 100%, 100%, 50%, 50%, multiply them out. It's 25% if you prefer to work in percentages. So there is a 25% chance of our babies being just the yellow belly het pied. There is a 100 times 100 times 50 times 50, which again is the 25% chance. There's a 25% chance that it will be het pied, yellow belly, pastel but not leopard. There's a 25% chance that it will be het for pied, yellow belly, not pastel, but also carry the leopard gene. And there is exactly the same probability of it not carrying the leopard and the pastel gene. So that's the outcome there, but you will see that from this pairing, whilst we do get our desired outcome in terms of hets, we will not get a yellow belly pied. All we will get is yellow belly het for pied. So what do we do with the babies that come out of this combination? We pick all of the yellow belly babies and we hold them back. We grow them up until they're sexually mature, so they are 100% heptapied with the yellow belly gene, and then we're going to breed them back to the father. So in 2 years' time or 3 years' time, we breed the father back to the yellow belly heptapieds. So we're going to take this guy and we're going to use his yellow belly heptapied offspring. My snakes are escaping here, so let me just put the lid back on them. So we're going to take this combination, we're going to take the heptapied with yellow belly in it, and we're going to breed it back to the pastel pied father. So let's remove all this. So 2 generations down the line, rather than in the first generation with the co-dominant genes, we are going to achieve our goal of getting the yellow belly pied. So we take the offspring, which are 100% heptapied. On the female side, we do need a female to pair back to the father, and the father is carrying 2 copies of the pied gene. And I'm running out of clips, so let's use these clips. Okay, now the babies are also going to be carrying the yellow belly gene. So we've selected a yellow belly 100% heptapied in the female, and we're going to breed it back to the father, who is also carrying a copy of the pastel gene, by the way. So we need another gene in this equation, don't we? Let's stick pastel in there. Okay, so the genes are all going to work independently, so we can remove the yellow belly and the pastel and just look at the pairing of the visual pied to the heptapied. So from the father, everything is going to be 1 copy. From the female, only 50% of the babies are going to get the copy. So we're going to get 2 visuals, 2 visual pieds, and 2 babies which are just heptapied. So automatically in that batch of eggs from that pairing, we only have 50% of the babies are going to be visual pieds. So right there we've reduced our odds by half. If we look at the yellow belly, the only one in the pairing that's carrying the yellow belly gene is the female. Remember, she is yellow belly heptapied. So 1 copy of the yellow belly gene. Let me just transfer this to our genetics table first. So pied is at the top, with 2 babies being visual pieds, 2 babies being 100% heptapied. Let's take yellow belly. So nothing in the male, 1 copy in the female. So 50% of the babies will carry the yellow belly gene. So when we look at yellow belly, 50% of the babies will have the gene and 50% of them will not. So let's transfer that to our genetics. But the male also carries a copy of pastel, so that is still actually in the equation for this outcome. We're pairing back to the father. He has 1 copy of pastel, and again you can see the outcome there is going to be 50%. So 50% of the babies will carry the pastel gene and 50% will not. So when we transfer that, there's the outcome. So our goal was to get a visual pied with yellow belly. So visual pied 50%, yellow belly 50%. So that's 25% probability of the babies being yellow belly pieds, and there is a 50% probability that it will not carry the pastel gene. 50% will, 50% will not. So we've got 50%, 50%, 25%, 50% not carrying the gene will be 12.5%. Okay, so that's half times a half is a quarter, times a half is an eighth. So 12.5% or 1/8 of the babies will be visual pied yellow belly. And that's our desired outcome. Okay guys, that's all for today. I hope you enjoyed it. I hope it made sense and helps you in your projects. We've had a look at some cool snakes, some cool projects that I'm working on. Don't forget to like and subscribe, and we'll see you next time.